Okay, welcome to the CUDA real-time path tracer. So essentially what you're looking at right now is a real-time path tracer running entirely on the GPU. So unlike a typical game engine, which fakes lighting using tricks and shortcuts, path tracer simulates how light actually behaves in the physical world. Every pixel on screen is the result of tracing thousands of light rays bouncing around the scene, calculated from scratch, every single frame. This was built from the ground up in CUDA, uh, the programming language that NVIDIA GPUs use. Um, yep, okay.
So next is how the path tracing works. When the renderer first starts, the image will look kind of noisy and like pixelated. Noise is actually meaningful because each pixel represents a random sample of possible light paths. The core idea is that every pixel on the screen has we fire a ray from the camera into the scene, and then that ray will hit the surface, and it will bounce in a random direction, hit another surface, bounce again, and so on until the set number of bounces. And if the ray eventually reaches the light source, it carries the light back to the pixel. If it doesn't, the pixel gets nothing from that passive speed blank. This will be done thousands of times per pixel, and all the results will get averaged together. And over time, the random noises will average out into a physically accurate image with shadows, reflections, color bleeding between the surfaces. All of it like emerges naturally from the physics. You can see it's happening right now as the image starts grainy and gets progressively cleaner as more samples accumulate. And you can press R at any point that will reset the accumulation and watch everything get recoded. Like that, yeah.
So the reason this runs in real time, or the reason this runs in real time is that rather than taking hours like traditional offline renderers, uh, let me rephrase that, sorry. Rather than taking hours like traditional offline renderers, this is all rendered in real time by the GPU. A modern CPU has maybe like 16 to 32 cores, whereas the GPU that I'm currently using, the NVIDIA RTX 3080 Ti, has over 10,000 cores running simultaneously. The way we use all of them is that each core handles exactly one pixel at 1920 by 1080 resolution. So that's over 2 million pixels computed in parallel every single frame. Every core is independently tracing rays, traversing geometry, evaluating lighting at the same time. GPU utilization during rendering stays above 95%. So that indicates the GPU is essentially never idle.
For the BVH exploration, the scene right now has over 240,000 triangles, and testing array against every triangle, every bounce would be impossibly slow. That would be billions of like intersection tests per frame. Instead, what's called a we built what's called a bounding volume hierarchy, or BVH. It's like it's like a filing cabinet. Instead of searching every drawer or document, you look at labels outside of each section and skip entire canvas that clearly don't contain what you're looking for. The BVH organizes all the triangles in the scene into a tree structure. When a ray gets fired, it only tests against a small subset of triangles, typically around 20 to 30, regardless of how many triangles the scene contains. This brings the intersection cost from linear to logarithmic, which means adding 10 times more triangles only adds a tiny fraction of extra work.
So the render supports full interactive camera control, as you've seen so far. So essentially, when we left click on the mouse and drag, we orbit around the scene, and we can use the scroll to zoom in and out, and then WASD to like have increment stepping, and then and as As the camera is moving, the image briefly goes noisy, then reconverges, and depending on the image, of course, and that's the accumulation buffer resetting. The render throws away the old samples because they're now from the wrong camera angle and immediately begins building up a clean image from the new viewpoint. On a still camera, the image converges to a near photographic quality within a few seconds.
Every rendering parameter can be changed live without restarting. The number keys control the bounce depth, or how many times each ray is allowed to reflect before giving up. With two bounces, the image will look very flat with very little indirect lighting, but with 8 bounces, the surface will pick up light that gets reflected off other surfaces, and you'll start seeing color bleeding, like walls tinting the nearby geometry and their color. Then F1, F2, and F3 switch between 3 lighting modes: sky only, areas lights with direct sampling, and a combined mode that samples both sky and area lights simultaneously using technology called multiple importance sampling, which reduces noise from scenes that have both types of illumination. Um, the bracket keys cycle through sky color presets, while blue sky, sunset, and night, each completely changing the mood of the scene. And P toggles the infinite ground plane on and off.
One of the more interesting interactive features is the dynamic point light, essentially a flashlight you can position anywhere in the scene in real time by pressing V to toggle it on, like this. And we can move this flashlight by, by holding V and dragging it with the mouse in any direction. So, and the plus minus keys control intensity of the flashlight. Uh, this is a physically correct point light. It falls off with the inverse square of distance, the same way real light does. Surfaces close to it are bright, surfaces far away receive almost nothing. It also casts physically accurate soft shadows. Notice how the shadow edges get softer when the light is close and harder when it's farther away.
And then the render also supports full texture mapping. When an OBJ file is loaded, the accompanying material file is parsed automatically. Each material texture gets loaded from a disk, resized to fit the GPU memory, and then uploaded as a CUDA texture object, which is hardware accelerated bilinear filtering directly on the GPU. The texture color modulates the surface during shading, so instead of flat gray surfaces, geometry picks up the albedo from the actual image map. All the lighting calculations apply on top of the texture color.
To summarize what this system does, the CPU loads the scene, builds the acceleration structure, and manages the window and user input. All of that is sequential, one task at a time. The GPU runs the path tracing kernel, 2 million parallel threads, each independently simultaneously physical light transport for 1 pixel every frame. Um, the result is displayed without ever copying pixel data back to the CPU. The GPU writes directly into shared memory buffer that OpenGL reads from, eliminating what would otherwise be a major performance bottleneck. Uh, at full 1080p with complex geometry, the GPU runs at above 95% perfect utilization, doing more physically meaningful work per clock cycle than any rasterization-based game running on the same hardware. This is the foundation of how next generation real-time rendering will work, where path tracing is already shipping in consumer games on this hardware. This project demonstrates the core architecture of that pipeline built from scratch. Thank you.